Thank you for the introduction. Oh, well, yeah. Well, I want to thank the organizer for inviting me for this talk. So the title is Solving Pmax R Satisfiability Above a Tight Lower Bound. So it kind of it expresses two aspects of our study. So one is, so the problem we consider here is a satisfiability problem, but not just a usual feasibility satisfiability problem, but we want to maximize the number of clauses that can be satisfied in a conjunctive normal form. So are you aware, so do you all know what conjunctive normal form means, CNF? So, yeah. Yeah. A conjunctive normal form is a formula of the following form. So this is a clause. So it's a set of literals. Literal is either a negation or a positive form of a variable. So here we take three variables, x1, x2, x3, and we can have either x1 or x1 negation, x2, x2 negation, x3, x3 negation. So they form literals for this formula. And we take a disjunction of a set of literals, and they form a clause. And this clause is and we take the conjunction of the clauses. So if these variables have one of the two values, either true or false. Or you can say it's 1, 0, or 1, minus 1. Whatever, it doesn't really matter, but it's basically a binary variable. So given us conjunctive normal form or CNF, what you want, the feasibility problem asks whether we can have a truth assignment for the variables so that we can satisfy all the clauses in the formula. This is a traditional satisfiability problem in the feasibility form. And so we can generalize the feasibility satisfiability problem by asking whether we can how many clauses we can satisfy. So maybe well, if there is a feasible solution for a given CNF formula, then the maximum number of satisfied clauses will be just the number of clauses in this formula. But maybe there is no satisfying truth assignment. In that case, we want to find a truth assignment for this formula that satisfies as many clauses as possible. This is a very well-studied problem, and it's especially, so just as tree satisfiability problem is important to study NP completeness and things like that, it's max tree satisfiability problem, which means we want to satisfy as many clauses as possible in a 3 CNF. 3 CNF means each clauses have at most 3 literals. In this case, each clauses have at most 2 literals, so it's 2 CNF. So 3 CNF is a kind of a standard flagship problem for approximation problems, and to classify the computational difficulty for approximation algorithms. So we are interested in max satisfiability problem, where each clauses have at most R literals, and we will study this problem from the parameterized complexity perspective. I'll explain about that later. This is a joint work with these prominent researchers, except for me. Yeah. Well, just as I said, maximum satisfiability problem is defined as given a CNF formula, find a truth assignment that satisfies as many clauses as possible. Of course, it's a very difficult problem because just as the maximum, the usual satisfiability, even when the clauses have at most 3 literals, is NP complete problem. So maximum satisfiability will be as hard as the feasibility problem, as you can expect. So, well, we can kind of restrict the maximum satisfiability into the following form. So we, instead of having any CNF formula, we can say the CNF, we want the CNF formula has, so each clause has at most R literals or exactly R literals. So in our study, we will consider a CNF formula where each clause has exactly R literals. But this problem is also very difficult. Two satisfiability problem where each clause has 2 literals. You can solve it in polynomial time to check the feasibility, but if you want to maximize the number of satisfied clauses, then it's really difficult. And it's one of the APX complete, what is called APX complete problem, which means it's hard to approximate above some given threshold for the constant of the approximation. So it's something like you can have a C approximation algorithm for max 2-set problem, but it's impossible to have C better than C approximation algorithm. So it's impossible to approximate max 2-set as close as to the optimal solution. So there is some threshold that you can get. So we are dealing with a hard problem, and there are several ways to deal with the hard problems, and one of the approach is what is called parameterized complexity. A parameterized problem, I will explain what it means later. A parameterized problem is fixed parameter tractable. We say fixed parameter tractable if there is an algorithm that runs in time of fk times n to the power of c. So fk can be very large. It can be exponential or bigger than exponential. But we want to have we want to have the exponent of n to be a constant. So if it's a hard problem, for example, if you're dealing with a vertex cover problem or satisfiability problem, then because unless P equal NP, it's hard to expect that you have a polynomial time algorithm which runs n to the power of c. So you should have something like 2 to the power of n or 2 to the power of 2 to the power of n or something like that. But if you can somehow restrict this combinatorial explosion in terms of k, and if you can somehow say that k is quite limited, then this algorithm will work better, run better than an algorithm of this form. So what we want to have is an algorithm that runs in the form of 2 to the power of k times n instead of 2 to the power of n. So for example, I'll talk about what parameterization means. Parameterization is a function from an input instance to some natural value. So, for example, if you have a vertex cover, then the input instance is given a graph and some k, and you ask whether there is a vertex cover of size at least k. And the natural parameterization here is k. So, and the best known algorithm for the vertex cover is of this form. So if k is usually quite small relative to the size of the whole graph, so if you have this algorithm, then in practice it can run quite fast.
So all star means your m
yeah.
is missing, right?
Yes, yeah, we suppress the polynomial factor like k or n here. So we just omit that factor and focus on this. Or if you consider Steiner tree problem, well, Steiner tree problem is a problem to find a minimum weight subgraph connecting k terminals. So k terminals are given. Yeah. Then there is a very classic algorithm that uses the dynamic programming, which runs 3 to the power of k, which has been improved to 2 to the power of k recently. So if you parameterize it by the size of terminal vertices, then it's a fixed parameter algorithm. K-path problems is again a fixed parameter. So yeah, it's a fixed parameter algorithm, so it's a fixed parameter tractable problem. But if every computationally hard problems have fixed parameter algorithm, then it's if every computationally hard problems have fixed parameter algorithm, then there is no point of saying that some problem is fixed parameter tractable. So fixed parameter tractability makes sense because there are some problems which is unlikely to be FPT. So one of the examples, so here we have some examples like independent set problem, heating set problem, or dominating set problem. So these are, so they are unlikely to be fixed parameter tractable in a similar sense that satisfiability problem is unlikely to be polynomial. So another thing we need to know about FPT is a concept called colonization. So it's similar to the polynomial transformation in the classic computational complexity theory, but the difference is, so it's a manual transformation from an instance to an instance that satisfies a similar condition as the polynomial transformation. But the difference is we want to bound the size of the reduced instance by a function of k. So we reduce a problem into something equivalent and small. So the next theorem is one of the central results in the parameterized complexity. So a parameterized problem belongs to FPT, so it allows a fixed parameter algorithm if and only if it allows a colonization. So it has something like that. Yeah, I'll give I'll briefly sketch what a colonization or kernel means using the example of vertex cover. Do you know vertex cover? Do you know what vertex cover problem is?
Set of vertices, right? Set of vertices looking at it.
Yeah.
It's set of vertices looking at it.
Yeah, it hits every edges. Yeah. So we want to answer the question whether there is a vertex cover of size at most k. Then we can formulate this problem into a integer linear programming formulation. And there is a well-known theorem that the integer linear programming formulation of a vertex cover has a half-integral optimal solution, which means there is an optimal solution where every variable has either 0 or 0.5 or 1, where each variable corresponds to the vertices. So because we can solve integer linear programming in polynomial time, we can easily partition the vertices of the graph into 3 parts. So one with 0, 0.5, and 1. And also there is a theorem that says there is an optimal vertex cover that contains all the vertices in this set and no vertices from this set. So partly they can contain these vertices. So let's say this set is V half, and this set is V1. Then the objective value of the integer linear programming is something like half times the cardinality of V1 over 2 plus V1, right? So it's a minimum, so this value is the lower bound of the optimal vertex cover. And here we can obtain, so if you take, because, and as I just said, because there is a optimal vertex cover that does not have any of these vertices, and all of these vertices and some of these vertices, we can bound the optimal vertex cover with V1 over 2 plus V1, which is bounded by this, times 2. So, well, I'll omit some technicalities, but it's easy to check that once you delete these vertices, then the size of these, okay.
I could understand the first inequality. The first one.
This one?
This one implies that there's a half inside. You multiply it with half, and it becomes bigger than the next one.
Multiply twice, 2, right?
Yeah.
Maybe that is 2. The half must be replaced by 2 in the left side.
Yeah. So it's.
Oh, sorry.
Yeah. Okay. So it's V1 over 2 plus 2. Okay. Yeah, I don't think it's not a good idea to go into 2D.
I cannot see that. Sorry.
Yeah. So, well, I think this inequality is obvious. So we can. So if V1 over 2 is more than K, then obviously optimal vertex cover is at least K, which means the instances does not satisfy our requirement. Then otherwise, it's like this. And there is some theory that, okay. So after, there is a theorem that the optimal vertex cover can be obtained by deleting these vertices, the vertices with O1, and by considering only the vertices in this set, and they have they are not connected to the set of vertices which has value equals 0. So we can just focus on this set. And so after that, because this is, if this is true, yeah. Because this is not true. If this is true, then we can just say no. Otherwise, the size of this set is bounded by 2k. So as a result, we have a statement something like either the instance is a no instance or there is a kernel. So we can reduce the problem into an instance which is equivalent and whose size is bounded by 2k. So this type of result is called colonization. And the final instance we obtained is called kernel. So that's the type of result I will present here. Okay. So we are, as I said, we are interested in the problem of max R set problem. So, and we want to have a sensible parameterization of the problem. So we can ask something like this. So is there a satisfying truth? Is there a truth assignment that satisfies at least k clauses? But it's not a good idea to ask such a question, because if you have a okay, I will explain why it's not a good idea to ask such a question. There is an approximation, a randomized approximation algorithm that satisfies at least this fraction of the given clauses. So, okay. Suppose we are given the following clause, and we take a random truth assignment for these variables. Then the possibility that this clause is not satisfied is 1 over 2 times 1 over 2. So the probability that the clause is satisfied is 1 minus 1 over 4, which is 3 over 4. In general, if you have R literals in a clause, then the probability that a random assignment can satisfy a clause is 1 minus 1 over 2 to the R. So, and you can easily de-randomize this randomized algorithm. So, well, okay, let's see the case when R equals 2. So it's always possible to satisfy 3 over 4 times m, where m is the number of clauses. So if the given k is less than 3 over 4 times m, then the answer is obviously yes. We can satisfy this number of clauses of the whole set. So we can obviously satisfy k clauses. Otherwise, it's something like this, which means the number of clauses is bounded by a function of k, which is a kernel by the definition of the kernel in the previous slide. So it's not a good idea. If you have such a concrete bound that you can satisfy in a given clauses, then it's not a good idea to just ask whether you can satisfy k clauses. So you need to have some different parameterization. So here we can instead ask, can you satisfy 3 over 4 times m, which is guaranteed, plus k clauses? So can we satisfy extra k clauses? That's the parameterization we choose here. Okay, so the problem we consider here is the following. Where F is a set of M clauses of size R, so having exactly R literals, and K is a non-negative integer, is there a truth assignment that satisfies this number of clauses? Okay. So the first thing we do is to represent the RCNF formula using some polynomial, or you can say random variable. So it's given like this. So it's for each clause you have this. So if you go back to the example, the first clause gives 1 minus 1 minus x1, 1 minus x2. And the second one gives 1 minus x1, 1 plus x2. So if it's a positive literal, then it's 1 minus something. And if it's a negative literal, then it's 1 plus something. So we define the random variable x in that way, and epsilon I is 1 if the corresponding variable appears in the same clause as a positive form, and it's minus 1 if it appears in the negative form. And it's a random variable because we want to randomly choose the xi's from minus 1 or 1. So minus 1 means it's assigned false, and 1 means it's assigned true. Okay, so if you have a formula something like that, then x's can be represented like this. So what information does it give? We can, if we set x1 equal 1, x3 equal 1, then everything becomes positive, and x becomes 5. And what it means is that we can satisfy extra x divided by 4 clauses. So, well, okay, that can be represented by the following lemma. So, given any truth assignment tau, the random variable x represented in this way is equal to the following number. So it basically computes how many extra clauses can be satisfied in a given CNF formula. So, okay. If you divide this by 2 to the power of r, then that is the number of satisfied clause minus the tight average equals x over 2 to the power of r. So in this case, we can satisfy we can have maximum x equal 5. That is, we can satisfy at most 5 over 4 extra clauses in this literal, in this CNF. So we kind of transform the problem. We transform the max R set problem into computing a maximum possible value of this polynomial, where xi is taken from 1 or minus 1. Okay. If you simplify this polynomial, then it will be of the following form. So it's basically a monomial in x multiplied by some constant ci for some subset of 1 to n. So what we want to do is, by setting xi equal to minus 1 or 1, we want to maximize this value. So intuitively, so this is a random variable that depends on this small x. So if the variance of x is large, then the distribution of x will be something like this. And we can also prove that the expected value of x equals 0. So if we have k somewhere here, and if the variance is large, then there will be some truth assignment that satisfies at least k. Of course, if the variance is, it is possible that the variance is very large, but the variance of the variance is also very large, so it's something like this. If the distribution is something like this, then we cannot achieve our goal. So this lemma tells us what's the necessary condition to say that we can have some So this lemma tells us that if we have these three conditions satisfied, then we can say that with some positive probability, x can be quite large. So there is a truth assignment that satisfies a lot of clauses, large enough clauses.
So this holds for any random variable?
Yeah, any random variable. So the expected value is 0, and the second moment is large. Well, it's positive, but the third condition says that the variance of the variance is limited somehow, so you don't have something like this, but it's more evenly distributed, so you have something like this. So these two conditions are combined to give that you still have some instance after some threshold. Like here we have.
What is B?
B is the constant here.
Any constant?
Yeah.
Positive?
It should be at least 1. Yeah, because you can compute it. You can easily check it. it's impossible to have smaller than 1. So that is, if you can express the second moment in terms of the size of the instance, so suppose you have something like this, then you can replace this part with the size of I, and if the instance is large enough, then it's a yes instance. Otherwise, so if you reverse the direction of the inequality, then the size of the instance is bounded and we have a kernel. Yeah. So the remaining thing is whether these conditions are satisfied and whether you can express the second moment in terms of the size of I. And okay, I'll not go into detail in this part, but it's possible to, it's straightforward to prove that the first moment is 0, and the Parseval theorem says the second moment can be computed in this way, where Ci is the constant here in each monomial, and the fourth moment can be actually bounded by the square of second moment, and the constant, so this is B, and the constant is 9 to the power of R.
So this inequality, who made this?
It's a well-known inequality. So it says it appears in Fourier transform analysis. Okay. So actually everything is here. So we just check that the 3 conditions are satisfied, and so we can have this, and the square root of the second moment can be represented in this way. So you replace this term from this formula, and then if you do some calculation, then you can at least say this. So the probability that x is as large as this one is positive. So if k is smaller than, so if you have k like this, then you have yes instance. So x is at least as large as k. Otherwise, s is bounded by some function of k. It doesn't necessarily mean that the original CNF formula has bounded number of variables or bounded number of clauses, but with there is some technical argument that says it implies that the original instance is bounded. So we have a kernel.
Here is just a number of monomials.
Yeah. But basically, each term has at most all variables. So with just that formula, we can say that there is at most R times O k square variables, which is a kernel. But actually, we can do better than that. So that basically establishes that makes our satisfiability problem is fixed parameter tractable. Okay, we have like 20 minutes. So this is a result for general R. But if you restrict R equal to, then we can do much better. Okay. So okay, well, I'll start from here. So, well, first we need to have some definition of some terminology. A variable is insignificant if for each literal y, the number of occurrences of the two clauses xy and x negation y are the same. So what it means is that whenever xy appears, we have x negation y. If this pairing happens for some variable x, then we say that's insignificant. And actually, it can be easily seen that in the polynomial that appeared here, and if you see the polynomial or the random variable x when r equals 2, then the insignificant variables that has this property is exactly the variables that does not appear in the variable, in this polynomial. So they somehow disappears when we simplify the formula. So that is, these variables do not affect to increase the number of satisfied clauses. So whether you set equal to 1 or -1, it does not affect the whole solution. So we can kind of ignore them. And significant variables are not those who are not insignificant. So the main theorem here is, well, let F be a true CNF formula which is irreducible in terms of semi-complete reduction. I'll explain about this later. And K is a non-negative integer. If F has more than 3K minus 2 significant variables, so significant variables which are not easy, which is not allowed to ignore, then the number of satisfied clauses is at least as large as that, which means F is a yes instance. So either it's a yes instance, otherwise it has less than 3K minus 2 significant variables. So if you just try every possible truth assignment for these 3K minus 1 variables, 3K minus 3 variables, and then you can find the truth assignment that satisfies my maximum number of clauses.
So what is size of F means number of clauses, right?
Yes.
And
It's M, yeah, M, number of clauses,
right.
yes.
And then you divide it by 4, and is it still bigger than K? So 3m plus 4 divided by 4.
3m. So this is the bound, this is the average and a bound that a random assignment can satisfy.
Ah, I see.
And then we want to satisfy 1 over K over 4 extra. Yeah.
We didn't. So did you have a K over 2 to the R initially?
Yes. So, but in this case, R equals 2, so is it? So, well, so this is the outline of the main theorem when R equals 2. We transform this problem into some graph problem, in an auxiliary graph. And we define some operations on this graph, and then using this operation try to ensure the existence of a subgraph with weight k. And we can, and there is a theorem that appears in the later slide, that if you have a subgraph in this graph with weight t is k, follow with some operation on G0 if necessary, then that means the original problem is a yes instance. And if you cannot ensure the weight k subgraph of G0, then we can also show that the maximum size of a matching is less than k. And using this information, we can kind of bound the number of vertices in G0, which gives us a kernel. So one thing we can use about the formula is that suppose that we have a formula of this form. Then we can make an equivalent formula by replacing every occurrence of negation of y with y, and every negation of y with every occurrence of y with negation of y. Then they are equivalent formula in the sense that if there is a truth assignment there that satisfies p clauses here, then there is a corresponding truth assignment that satisfies p clauses. If you just reverse the truth value, then that will work. So we can define a switch of a variable, and that can be naturally extended into a switching of a set of variables. And we define fx to be a formula that is obtained from f by switching the set of variables in x. And so this lemma follows. So instead of trying to assign false value to some variables, we just set true values and try to just switch some variables if necessary. So assigning false variable is replaced by switching. And we basically think that every variable we are interested in is either set equal true or true with probability 1/2.
So you want to make some random choice for each variable. Is that what you want to make some random choices for each variable?
Yeah. Okay.
So say like either x is true or just switch x and then make it true, or is that?
Oh, sorry.
No. Okay, let's continue. Yeah, we'll see.
So what I'm saying is, I just mentioned the polynomial or the random variable x, and that computes the number of satisfied clauses by a truth assignment, by a deterministic truth assignment. Okay. But if you slightly modify this formula of x, then the modified version can give us the expected value of the number of satisfied clause by a random assignment. And the random assignment okay, I'll just skip this part. Yeah, well, that will somehow appear in the later part. So, so we want to transform this formula into a graph problem, which is to find the maximum weight subgraph. So the main lemma here is, for each subset of R, we have there is a truth assignment that satisfies at least this number of clauses, where KR equals this. So this formula is basically obtained by some modification of the polynomial of x, but it's a bit of technicality. So, but the main implication here is that this is basically focused in R and the relations between vertices of R. So that gives us to interpret this formula into a graph. So we define a graph where vertices correspond to the variables and the edges correspond to the pair of vertices that appear in some clauses. And this part becomes the weight on the vertex, and this part becomes the weight on the edges. So if you define a graph like this, okay, yeah, okay, this formula is obtained by fixing every variables of x, every variables of R equal 1, and every other vertices of other than R equal true with probability half. So it kind of neutralizes all the vertices outside R and set every vertices of R equal true. And because we know that switching a vertex corresponds to making the same variable into false, we can use this formula. So
So weight of the subgraph is sum of the weights on the vertices and edges.
yes. So we can define a graph like this, and there is a weight on the edges and vertices. Something like this. And we are allowed to switch the vertices, which corresponds to switching the variables. And if you switch the variables, that means we set it into false. But in the switched formula, it's just set to true. So instead of mixing with true and false value, we can just switch the variables. And so by switching some of the vertices, if possible, we want to find the maximum. We want to find a subgraph with a maximum weight. So how we do this? So here we use the induced tree structure. It can be. It's easy to see that if you have an induced tree, so there is no edge between these vertices, and if you have some weight here, then there is a set of switches. There is a set of vertices whose switching gives us every edge with positive weight. Oh, okay. I forgot something. Well, if you switch a variable or switch a vertex in the corresponding graph, then if you switch this vertex, then the weight of this vertex becomes -1, and all the edges, all the incident edges become +1. So the size of all the incident edges becomes reversed. So given this, so in this graph, this edge has a negative weight, so we want to make it positive. Then you can flip this part, this vertex, and then make it positive, and this one negative. So in this way, if it's an induced tree, then it's possible that every edge becomes positive. And some of the vertices will be negative. But if you just switch all the vertices at the same time by random chance, then the effect of the vertices will be neutralized. So in other words, the expected value of the weights on vertices will be 0. But the weights of the edges will remain the same because both endpoints of the edges is flipped, it's switched, so its sign changes twice, so it remains the same. So if it's an induced tree, then we can find a set of vertices such that whose flip gives us a weight at least as large as the number of edges in the tree. And we can assume that the weights on the vertices are 0. And if you have a collection of a vertex disjoint induced trees, then you can do the same thing for each of the induced trees. So we can assume that the weight of each of these induced trees is as large as the number of edges in it, and then take a independent random switching. So if you have a vertex disjoint of trees like this, then there may be edges between these trees. But if you take a random switching of these two graphs, then the effect of the edges between these two structures is neutralized. So we can assume that the weights, the expected value of the weights is equals 0. So we can kind of ignore the edges. So as a result, if you have a disjoint set of induced trees whose number of edges inside each of them is at least k, then the answer is yes. Otherwise, that implies we do not have a matching of size at least k. Because matching of size k is a set of k-induced trees. So we can use so there is a famous formula, Todtborch formula, which characterizes the maximum size matching in a graph. So that formula gives us that this number is less than k because we don't have a k matching. And if you just manipulate this, yeah. So, okay. So it's not difficult to see that if you can just prove that the number of odd components in G0 minus S, where S satisfies this formula, satisfies that, then we are done. And yeah, it's not difficult to see that this is true. So that gives us that the size of the graph is bounded by 3k minus 2, so which gives us a linear kernel.
It's quadratic.
No, it's linear kernel.
Is it?
Yeah. Linear. So okay. So
Number of edges.
0 minus number of insignificant vertices. But basically, we can say that the number of we can also prove that the number of insignificant variables is bounded by 1, actually. So they can be regarded as just the same thing, because they don't have any effect on the formula. Well, yeah, that's it. So, yeah, thank you.
Thank you very much. Are there any questions? Okay.